we have presentations again. And the way I organized the calendar of the presentation, I followed, I took several criteria into consideration about topic and other things. However, I am not opposed to use swapping if needed. And in particular, I think Stephanie, who is scheduled to present next week, if she hasn't changed her mind, but I think she's still looking for somebody potentially to swap with her. So if somebody wants to present sooner rather than later, talk to her. I asked that you use obviously this is about the graduate students, right? So I asked that you use the same discussion forums that we use for organizing these things, assigning topics, so that we have a record of who has swapped, who has agreed to what. And if you agree with each other to swap, then I will honor that. Just I expect, the person to show up on time and present. I just need to know in advance, though. So that's one thing. This week, I will give some readings to help you, to study for the material I'm showing today. But I am not going to assign a discussion about it for two reasons. One is to go a little easy on the people who present next week, so they so that they don't have yet another paper discussion and questions, so that they can prioritize as needed. And the other reason is that I would like you instead to start using the extended discussion that I already opened, which similar to what we did before the last midterm. The week before that midterm, there was no new assignment, right? There was just a week-long discussion where you can open threads and ask questions and ask and answer questions to each other. And then I would interject as needed. So I want to do this again, but instead of starting next week, which would be the 1 week before the test, I want, already started the last week in response to the feedback you gave me last time that you wanted something that was more extended. So start using that, including this week. I believe I get 20 points on that, and I'm thinking actually of raising it to 30, so that, really you should use this for, at least ask some questions and at least answer some questions of your peers. So some of you didn't do it last time. You lost a lot of points, and it was just a pity. So those two things, basically. If you want to swap, but leave a record on that discussion. No, there's going to be an assignment that goes into your study for the test, but I don't ask you to comment, but I ask you to start raising questions on the material before the second test. All clear? All right, and Stephanie, actually, I encouraged her to even ask that question, whether somebody wants to swap with her. She has good reasons for doing that, and she put it in the chat. So if it's easier to come to an agreement on the chat, it's good. But then please leave a message on the discussion board too. All right, well, let's start today. So, the course is called Space and Time in the Brain, right? And say, well, where's time? Because we haven't really gotten to it. I mean, we touched time in different ways, but we never really, we talked a lot about space. Part of it was, this being a new course, I didn't have a good sense of how fast I should go. So sometimes I would cut my lecture short, reorganize the material. Kind of the philosophy was it's better to do maybe one less thing, but try to do what we do to make it very clear. And so in a way, when we got to the time argument, it kept kind of pushing down. It was always meant to be a little smaller than the space, but we got here today. And so we are going to talk about time in the hippocampus related to place cells and grid cells and other cells that are in the hippocampus. And in particular, we'll cover it in two ways that are not really strictly related, two ways of thinking about time. One is what is written here, temporal codes of position in spatial cells. And so it's a way in which time matters in the way that cells encode information about space. So we've seen things getting encoded by the firing rate of a cell, but there are other ways to encode information in the activity of neurons. And so that's also a very important topic because it has to do about neural codes, how the brain codify information in the activity of its cells, which is a recurring theme in this course, but it's really a fundamental question in neuroscience, right? And the other, so we start with that. And then the other is really the encoding of time. How does the brain encodes time, if any, which is a big question asked to a lot of different brain areas. There's a lot of different ideas. But since this is a course that we kind of focus a little bit on the hippocampus, we'll look at what we know about that related to place cells and grid cells, and whether these cells can encode time and not just space. So we'll start with the first one, temporal codes of position in spatial cells. So in a way, we're looping back to theta. Remember, we discussed about local field potential at the very first lecture, what it means to filter the signal from the brain, low pass filter, we get this collective signal, the signal that is reflective of collective activity of the cells in the hippocampus. And we looked at different patterns, and we related different behaviors. So, and we saw last week how sharp wave ripples in local field potential relate to certain kind of behavior, certain kind of properties of place cells like replay, for example. And in a way now we're doing something similar about theta. So we remember theta is about locomotion or attention. We had T theta, A theta. T theta was about translation. So it was about the rat running around. When the rat runs around, there is this theta mode in the local field potential, which is very rhythmic, like usually 8 to 12 hertz. And we looked at different functions and we discussed them briefly. And one of them was this about the temporal coding scheme. This is really like the old slide, the neural coding scheme. For example, via phase precession in place cells, which will, this is, there's a typo here. The old slide said, which we will study later in this course. And now I'm saying we should study now, today. So before, let's just kind of give a little bit of a refresher of basic stuff that you must have seen in basic math in classes, either math, physics, whatever, even in high school. So the idea that you can have an oscillatory signal, it's like a cosine. So you can represent it as a function like x equal x0 cosine omega t. Basically, omega t is the angle, and it's composed by the angular frequency that is in hertz multiplied by the time. So as time passes by, based on this omega t, the angle changes because it's multiplied by time. And as the angle changes, the cosine takes different values. And so you have a cosine, you have an oscillations, right? And the maximum amplitude would be x0, which is when cosine gets at 1. The amplitude, which is, the peak amplitude, sometimes I called it in other circumstances, is x0. The big T would be the period. So going from peak to peak, the full cycle of the oscillation. And we have these properties in which, basically you have that the angular frequency is like 2 pi divided by the long period, because after that, the angle basically becomes the same. And so you have a new cycle. So you go from 0 to 2 pi, and then again, you start again. It's like going from 0 to 360 degrees. 360 degrees is equal to 0, basically, and you complete the cycle, and then you have another cycle. And as that angle goes from 0 to 360 degrees, the cosine goes from 1, then -1, then it goes back to 1, right? And then this would be 2 pi, and it has to be equivalent to the period of the oscillation. And the frequency would be the inverse of the period. So if the period is long, then the frequency is low, and vice versa. So kind of similar to what we were looking at when we were looking at grid cells, but in space. This would be in time. So this is a way you can represent, an oscillatory signal, a periodic signal with a cosine. And then we can talk about the phase of this oscillation, which basically would be, for our purposes, it would be as this angle that, this is time. As time passes by, the time modifies this angle inside the cosine, and so that would be the phase. So if you're looking at these in the form of angles here, you go from 0 to 0.5 pi, and 3 seconds of a pi, and then 2 pi. And so you get these signals, and as this angle grows, the signal takes different phases. So the phase is basically the way that this angle marks the progress through the cycle of this signal, this periodic signal. And here there is 2 different signals in blue and red. They're offset by 90 degrees. So that would be like a phase shift of 90 degrees. But, really you want to think about the phase would be the stage during the full cycle at which this signal is. And it's important to think about it, because then we can talk about the phase of theta, okay? And we can think about something that we never really looked at until this late in the course, is like, what do if you have a place cell that fires in a place field, how does that relate to theta? Like you have theta, and that's a log field potential, okay? This collective activity. But then when you look at a single place cell, or, would be a pyramidal neuron, or maybe you could even look at an interneuron. What happens when, do the spikes occur everywhere during the cycle of theta? So remember, theta, it can be like, so let's say the theta is 8 to 12 hertz. So let's just imagine 10 hertz. So you have a full cycle every 100 milliseconds, right? That's not the time scale at which we looked at things during this course. We look at the running around, and the cell spikes, and then we look at the spikes, and the spikes occur always in the same spot. And then we do an average of firing rate, and we compute rate maps. So what is really happening on a fine time scale of theta, over a cycle of theta that lasts 100 milliseconds? Do the spikes occur everywhere? Does it matter? And so it turns out that theta modulates the firing of place cells. So if you look at theta here, and here's 2 cycles of theta, okay, just so that to make things clear. And then you look at the firing probability of pyramidal cells, so a place cell. So you look, okay, going from, say, here to here is like about 100 milliseconds here, right? And then from here to here, another 100 milliseconds. You look at like over many, many cycles, okay? And you look at when the cell was firing relative to the phase of theta. So the phase could be like 0 degree, then 180 degree, then 360 degrees, all the angles in between, right? And you see, you have an histogram here. You see the distribution of firing. Look at the y-axis is firing probability. And on the x-axis, we have theta phase, right? Because it's the cycle of theta. You can see that the cell fire a lot more in the, the zero, the zero phase of theta. That here, basically, it's represented more like as a sinusoid, not a cosine, but as a sine, right? Because it starts at 0. The cosine at 0 is 1, the sine at 0 is 0. It just really doesn't matter. It's just offset by 90 degrees, basically. But basically, what you're seeing is that there are phases of theta when the cell tends to fire more. The firing probability goes up. And there are other kinds of cells that also are modulated, but the phases of theta when they are most likely to fire are different. So these are 3 different classes of interneurons, and you see that there are different phases of theta. So this cell fires almost with the same phase of pyramidal cells. So pyramidal cells would be like principal neurons, or what place cells are. These are interneurons. And so the interneurons tend to fire in opposition of phase than place cells, or in this case, it's the same phase. So there is really a complex interaction of when cells are firing during this cycle of theta. It's like there is a dance there. When place cells and interneurons fire, they fire at different point during the cycle of theta. They influence each other. It's a complex network. It's a circuit that is producing these temporally patterned behaviors. So basically, this is just to say that we haven't looked at interneurons much during this course. So, really the most interesting part is this one, the pyramidal cells, because this is place cells do. If you look at the place cell, the cells tend to fire more at certain phases of theta and not others, okay? So this is something we didn't know before, we didn't cover before. It's really something you can only look at if you're looking at really intervals of time of 100 milliseconds according to the cycles of theta. But there is more than that. There is a really striking property of how place cells fire during theta. This is probably one of the most important, even if it's observation, experimental observation. And guess who did that? Also John O'Keefe. So I would say John O'Keefe, got the Nobel Prize. I would say that after the discovery of place cells, I think the discovery of what we're about to see, phase precession, is probably just very important thing that he discovered. And we don't really know well phase precession, but it's really something striking that is influencing the way we think about this part of the brain. So what is phase precession? Okay, let's think about the animal running on a linear track, right? We've seen this so many times. Let's just say you have a place cell. Okay, you have a place cell, so there is a firing field, there is a place field. Usually we call them place fields, but this figure calls it firing field, same thing. Here, where the cell fires a lot. Okay, well, we knew that already. Here, that goes from 0 to almost 40 hertz of spiking when the animal goes through this particular region. That cell fires. That's a place cell. That's what we've always seen so far. Okay, now let's look at really how it's firing. Every cycle of theta, where theta, remember, is being acquired through pretty much the same area of the brain, but through that low pass filter that tells us about the collective activity. So you have the cycles of theta. So you look here, what is happening here, just this part gets expanded, and on a single run, this is a rate map, so it's made of many runs, but on a single run, you get theta. You see this rhythmic theta. This is 200 milliseconds. And now, so you put these marks here, where each cycle of theta, the gray lines, and now you look at where the spike occurs as the animal runs through the field once. And you see these red little ticks are where the spike occur. And now you can see that what's happening is that the spikes occur earlier and earlier in phase relative to the phase of theta. So if you look at like these two spikes here occurred almost at the peak of theta, okay? These two, but now it starts moving more toward the left to the point, if you see from one cycle to another, these three spikes now, because this is where the animal is really at the peak of the firing rate of that cell, occurs not at the peak of theta, but earlier on. And so you see that basically by the time it gets to the end of the field, these last spikes occur not at the peak here of theta, but all the way back, right? So you just have this weird thing. It's called precession, right? Precession that precesses. So you have two phenomena here. One is that the firing rate goes up because as it goes into the field, you have the peak of the field. So the spikes tend to be more and more spikes, these bars of spikes. But the position of the spike relative to this theta clock, the theta clock that you have under, they occur earlier and earlier in phase. They move, they shift relative to the cycle. They don't occur always on the same part of the cycle. And so what happens is that you can think of what we've seen so far in this course is what is called a rate code. It's called a rate code because basically what we've seen is that we know where the animal is based on which cell is fighting and how much. So if this cell is now silent here and now it's fighting, you know that the animal is in the fighting field, right? So there is an encoding of space. It's space that is represented by the firing of that cell. You know what when it fires, and it fires a lot, the animal is in the place field. This is what we've seen for weeks, right? But now we're seeing something new. Is that there is additional information, because if you look, not just how much the cell is firing, if you really look at where, rather when the spikes, the single spikes occur, happen relative to the oscillations of theta, then you know even a little more, because now you know how much progress the animal has made through the field. Now you can say, well, I can kind of say that too, because it depends on the firing rate. The firing rate tends to go up. Yes, but it's not really that precise. Here you have like this additional way of encoding the progress, which is based on where these spikes occur during theta. They start one point of the cycle, and then they keep moving up, and they move shift relative to the phase of the cycle. So basically, now there is additional positional information that is not conveyed by how much the cell is firing. It's conveyed by the timing of the spikes. And so that's why it's a temporal code. It's a temporal code. It's a way of representing information that depends on when spike occurs. It's a temporal code. And in particular, this particular kind of temporal code is called phase code. Well, because it depends on the phase of the spikes, okay? This appears to be a pattern in the firing field shifting from multiple spikes to two. Well, it's because the firing rate goes up and down. It waxes and wanes during the field, right? So if you look at all the rate maps that we've been seeing, at the periphery of the place field, the firing rate is low, in the middle is higher, right? Because this basically means that the firing rate tends to go up, so you're gonna get more spikes in the central area of the region. I say, but it starts with 2 though. Well, yeah, I mean, it's every trial is a little different. When we look at the place field, is an average of many trials, right? Does that answer the question? Or comment by Jacek? Okay. The firing field temporal code. Yes, this is space. This is space. And this is the firing field computed by many, many trials. This is when the rat is running once, right? This is the firing rate map computed by many times that the rat runs on it. It's an average, it's an histogram. It's like how, you look now at a single run and you look at the spikes that occur during the single run, you look at them. Okay, this is what happens from theta cycle to theta cycle. These spikes tend to move. It's as if, the previous slide told us that the firing of the place cell is also rhythmic. But here it's as if the rhythmicity is also in the theta range, but it happens to be a little faster than the actual theta, the local field potential theta. So you got theta, there is 1 theta when the animal runs around, and then you get the particular firing of a place cell that might be active or not, depending on where the animal is. If it's active, now you look at when it fires, when the animal traverses its place field, it can fire also, it kind of fires rhythmically, but this rhythm is a little faster basically than theta. And I says, why is that? How come that this is, how is this computed? What is it telling us about the brain? So, here basically I'm just showing different plots that you could say, well, does it correlate with the progress that the animal does as it runs through the field? Or is it time? It could be time, right? Because the animal takes some time to go through. Or is it like a correlation of how much the cell is fighting because it changes throughout the field? And so you can correlate this thing. You can correlate the phase of the spike here with the position, with time, with firing rate, and compute the correlation. And you see that the correlation is much higher for position than time or instantaneous firing rate. So basically this is telling us that this phase precession of spikes is really providing some information about the progress that the animal makes through the field in that particular time occasion that it is traversing that area. So how does that work? Well, there is a very popular model that is based on what you might have seen in physics called oscillatory interference. So you can go on YouTube and find audio. I'm not going to try to do it because it's just difficult. So like if you have a sound wave 1 and a sound wave 2, if they have a slightly different frequency, different pitches, but very close, what you're gonna hear is something that is a pitch that is kind of close to those two, but the intensity, the amplitude of the sound comes up and down, up and down. So you hear like, one of these sound wave would be like beep, like a beep, constant beep. The other would be a slightly different pitch. But if you have them at the same time, what you're gonna hear is that they're just gonna interfere with each other so that you hear a beep that the volume goes up and down. And we'll see for a second why that is. And this is some math refresher. This is exactly the same plot that I put before. I just put it here just as a recollection of all the parameters of a wave. So let's look at why this happens. Well, you get, say, one wave that is this, another wave that is this. So there are two cosine, omega 1, omega 2. So omega 1, omega 2 are slightly different, okay? So you have kind of like two sounds with two pitches. Well, because they're slightly different frequencies, they cannot be perfectly aligned, right? So occasionally they will catch up with each other and they will be perfectly in phase. See, the peak here is coincident in time with the peak here. But because I think the blue one here is a little faster, they will get off phase quickly. And at some point, you're going to have the green is at the peak and the blue is at the trough. So this is a positive peak. This is basically a negative peak, right? And that's just because one goes a little faster than the other. So every now and then, they will catch up with each other, and then they will go out of phase, and then they will get back in phase, and then get back in phase. Every so many cycles, you're gonna have that these two waves, they're gonna be off phase and then in phase, and off phase and then in phase, and off phase and then in phase. And then you see what's happening, right? Beat. Basically, what happens is that when they're in phase, they're going to have what is called constructive interference because they're both at the peak, so they sound, and so you're going to get high intensity. But when they're off phase, they're kind of subtracting each other out. And so you're going to get basically to zero, which is destructive interference. And then you're going to have all the things in between that are sort of halfway. So this is what happened when you sum the two signals, you get something like this. And so you have a signal that is double oscillatory. You know, it's oscillatory in two ways. One is the fact that it's a wave that goes up and down, and it does this with a frequency that is very similar to these two ones. And the other is that the amplitude goes up and then down and up and then down in a much slower time scale, right? And that's called the beat. So you just need to do trigonometry, sum these two, and you sum these two, you do trigonometry, you get this function, okay? And you see that this is the product of two cosines, one that has a slow frequency and one that is a high frequency. The high frequency, here, I'll give you the formula, is called the carrier frequency. It's this frequency here, right? If you follow, goes up and down, 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 up and down. And that one is, the high frequency is basically the average of the two. So the frequency of this compounded signal would be at a frequency that is the average between these two. So it's right in between, right? One is a little slower, one is a little faster. It's somewhere in between. Not somewhere, it's actually in between. It's really half of the sum, it's the average. And so that's the carrier frequency, is this one that goes up and down fast. But then you have to multiply this by another cosine that has a low frequency, and is basically this frequency here would be half of the difference. So say that one is 8 hertz and the other is 7 hertz. The carrier is going to be 7.5 hertz, so very little difference. But this slower amplitude oscillation will be half of the difference, so 0.5 hertz, so way more slower. This is the beat frequency. Okay, have fun, go on YouTube, find one, just listen to the audio. But what does this have to do with phase precession? Well, this phenomenon that is like so unrelated to everything we've done could be a mechanism by which cells not only produce what we just saw, phase precession, but also produce multiple spatial fields in space, like a grid cell. So it's possible that phase precession and being a grid cell, because I don't know if I told you, but phase precession is also observed in grid cells. Not always, but basically it's like maybe that's a hint that this phenomenon is what generates grid cells. in a way, phase precession and the multiple fields of grid cells are two aspects of the same phenomenon. Well, let's look why. Well, actually, I have this intermediate slide that I'm not going to go over extensively because it's basically the same thing that I showed you in the previous slide. I really wanted you to understand this part. So it's just a different way of putting it. Like here, we put the green and the blue one on top of each other to see the alignment. Here, there is really a superposition, okay? Here, they draw it in red and blue. And you see there's slightly different frequencies. So every now and then, they perfectly coincide, and then they go off phase, and then they catch up again. And so when they are in perfectly opposition of phase, you have this destructive interference. And when it's constructive interference, and that corresponds to the low amplitude and high amplitude. Exactly what we just saw, just so that when you see put one on top of the other, you know, you see it better. But then I don't know which one you see better. So I'll give you like, okay, I'll give you both so that. But let's go to this idea that you can make a grid pattern in space while you're doing phase precession in time. Okay. So how does that work? Okay, let's just assume the rat is moving through a linear track, okay? And from a grid cell, we can kind of expect to have repeating place fields. So this would be like what occurs in terms of firing rate, okay? So what we always see, let's just assume the animal is running at a constant speed, let's say 30 centimeters per second, okay? This is distance. So the animal is moving in about 1 second. It goes from the end of one field to the end of the other field, the full cycle. Now the cycle here is space though, right? Because grid cells are, you know, repeating in space. The animal goes back in space and it fires again. So, you know, grid cells are periodic, and we say we are periodic signal. But it's in space, not in time. We've seen this and talked about space, but now we're talking about time, and we're talking about oscillations in time and tether in time. What we're about to see here is how the oscillations in time get converted into oscillations in space, which would be like the firing of grid cells, okay? So let's just say you have two slightly different frequencies of theta. One is 7 hertz and another is 8 hertz. Let's just assume that this is theta as you recorded from your electrode, you know, as we've seen, the local field potential. But let's just assume that the particular place cell here also has its own internal frequency, okay? And that this internal frequency is a little faster. It's about 8 hertz, okay? So let's just assume these two electric traces, activity of membrane potential, or in other physiological forms, I'm not going to go into that. They interfere exactly the same way that we've seen for the interference. Well, now you're going to end up with a signal with an activity inside the cell that goes up and down like those beats and carrier frequency that we've seen, right? This blue trace here. And so if you have a spike threshold, meaning when the activity goes above a certain threshold, the cell spikes, which is what happens in the Hodgkin-Huxley model or in the integrated fire model, you know, whatever model you've seen about the generation of spikes in whatever introductory neuroscience course you've done, like you know that when the activity depolarizes in the cell, if it reaches a certain threshold, then you have the generation of an action potential. So if this is the activity here, whenever it starts crossing a threshold, now you start making spikes here, you see? And so these would be the spikes that when you average them in a rate map, it would make a place field here. So basically, if the run is running at a constant speed, because of the interference of these two theta signals, the main theta signal at the internal theta signal of the cell. They would beat, they would produce this low oscillation, and because the rat is running at constant speed, time and space oscillations are now related. You would, as they are running around, you would have this cell firing at spots that are at the same distance, like a grid cell, right? So what is missing here? What is missing is that we are assuming that the animal is running at a constant speed. That's why you have something that is periodic in time becomes periodic in space, because the rat always takes the same amount of time to go from one vertex to the other vertex of the grid. But in reality, that's not how it works. Like now, the animal can go around at whatever speed they want, they change speed, they stop, they restart, and grid cells still fire as grid cells. So the same cell has its own vertices. We know that from a rate map, the cell will be active again when the animal goes in the same spot. So what is missing from this model is that this difference between these two frequencies has to depend on speed. If you make this difference in frequencies depend on speed, so that when the animal is running a little faster, this difference of frequency becomes a little larger. Now you're going to find that this beat and these oscillations, these low oscillations and the fighting activity remains stable in space, which is what we want from a grid cell. So the rat might go really fast from here to here, but then really slow from here to here. And still the cell will fight again at the same distance. Time doesn't matter anymore, only distance. And that's because we made these different, this difference in frequencies depend on the speed. And I'm not really showing you how, because we would have to show it mathematically. But one way to think about it, if you know about, space position is the integral. For those of you who are more familiar with calculus, is the integral of speed, right? Well, in the same way, the phase is the integral or angular velocity. And angular velocity, if you change it based on speed, so basically you're letting this mechanism become an integral of speed. And that will give you the position stable in space. If that made sense to you and helped you understand it because you have a good physics, mathematics background, good. If you didn't understand this last thing I said, don't worry, that's just one way to think about this. But the other way to think about this is just like intuitively, if you let these different frequencies come in and out of phase as a function of speed, then the time that one of the wave takes to catch up with the other, because it depends on speed, now you end up with spatially stable grid. I have something here written here that I need to move up, but basically it's just what I just said. And so not only this explains grid cells, it also explains phase precession, because if you look at where these spikes occurred, now you imagine you're the experimenter, right? This is all a model. You don't see it. What you see is these spikes, and then what you see is this theta, because that's what the orange one, that's what you record. Now, if you look at where they happen in terms of phase, you'll see that they phase precess. So that if you look at phase and time, you see that these spikes, it intersect the theta signal at different phases. And so it kind of decreases here. So this, that doesn't have, it's a physical phenomenon studied in other circumstances, has been taken to be possibly a mechanism for producing both grid cells and phase precession, or rather phase precession is in a way, a kind of collateral effect in a way of this mechanism. But we don't know if it's the fact that cells fight as grid cells is a collateral effect of phase precession, or if it's phase precession is a collateral effect of cells doing grid cells, because you don't know what the brain is really taking, caring about. Right. So one thing that this model predicts, you remember that at different depths of the medial internal cortex, from dorsal to ventral, you find grid cells that have different scale, right? Different frequencies. So that would say, okay, that means that the internal frequency, the intrinsic frequency of cells should change so that you can make grid cells at different scale, right? And so they did an experiment. This is in brain slices, in which they inputted the current into cells of the medial internal cortex. That it's called a chirp. It goes from slower then to much faster frequency. So it basically goes from slow to high frequency. And now you look at what the cell, how the cell responds in terms of membrane potential. And you see that the ones that are ventral responds in amplitude, resonates better when the frequency is still slow, while the ones that are more high up here, like more dorsal, they tend to resonate better with frequencies that are a little higher. See, when this signal becomes more frequent, this is the input. So a cell that is more ventral has more amplitude here, a cell that is more dorsal has more amplitude here. And that kind of matches what we know about the pattern of the grid. So this is kind of a prediction of the model that was confirmed. If it's true that grid patterns are made of interference, then you would expect that the intrinsic frequency of cells that are more ventral should be lower because of the mechanism that we just saw, basically. There's just no way of converting that time frequency into spatial frequency, okay? Now, what I say here about resonance is also another physics concept, and I don't want to go into physics, but just so that I give you a sense, like systems have sometimes a natural frequency. You know this from pushing somebody on a, when it's swing chair. If you push them, at some point you gotta push them at the right time every time. And that's easy. If you start pushing them at the wrong time, you will stop, you will interfere, you will disrupt, and the child is not gonna like it at all, right? So you must have had that experience. You gotta go with the right timing. So that depends on the length of the rope, and so it's like a system that resonates at the right frequency of input. Same thing when you have a fork here. The time that you use, say, for example, for tuning an instrument, if you hit one, then the other one is going to start resonating too. If you play guitar, you put two different strings on the same note, the same pitch, and you pick one, the other one also is going to start kind of resonating. It's a problem for engineers when they build bridges, because the bridge is going to have its own resonating properties. So like if you have the resonating frequency, the natural frequency, if the natural frequency is the same, say, that people use for walking, and you have a lot of people walking at the same step, and that step happens to be the natural frequency of the bridge is going to start oscillating like crazy, and it's going, it has been known that the bridge can collapse. That's why the engineers try to make sure that the structure doesn't have a natural frequency anywhere close to that, or anything that the bridge might be subject to. And that's also why I believe in the army, if you are marching on a bridge, you break ranks and you stop marching altogether so that everybody is walking at its own pace. There's not a single pace, and there's no risk of trying to, hit the natural frequency and breaking the bridge. Although people then also have their own tendency of, if the bridge starts oscillating, to also walk with that oscillation. So you might have noticed that too sometimes on a bridge, on a small bridge. The Millennium Bridge opened in 2000 in London. They had to close it down right away. This was a major artistic, architectural piece built in London over the Thames Bridge. It had to be closed down right away. It was closed for years to fix it because there has a natural frequency with people stepping on it. So people were stepping on it. This was oscillating. Anyways, just to say that's resonance. It's the same thing what we're seeing here. You give an input current at different frequencies, and based on which is the natural frequency of the cell, it will amplify the oscillations when this chirp signal is getting at the right frequency. And so you see these different resonance frequencies for different grid cells, as you would expect if grid cells were making the grid pattern based on this phase, based on the oscillatory interference model that we've seen. So briefly, I want to say, okay, but how do you make hexagonal grids? So we're seeing this thing as an animal going on a linear track, right? But in 2D, you have a grid cell is made an hexagonal structure. How do you make the hexagonal structure? Well, if this animal has this system that we just saw going through a linear track here, so you have these frequency that depends on speed on a single direction. In open space, in a two-dimensional environments like a square, you would see bands like this, depending on the direction. So it doesn't matter which direction the animal goes. If this is something that changes its frequency based on speed in only that direction, the way it works basically is that when the animal is going, say, in the perpendicular direction, there's no change of frequency, there's no change of difference in frequency, and so you get the same amplitude. And so what would be like repeating firing patterns like this would become bands. So you would expect something like a cell that produces bands, okay? If you have 3 of them at would be 60 degrees and you sum them up, you would end up with an hexagonal grid, which would be like, would give you a grid cell. So that would be basically the model. And it requires finding cells that oscillates really fast at theta, and that the exact frequency depends on the speed and direction. Remember, speed and direction means velocity. So the velocity, the vector of velocity, or depending on which direction the animal is going and how fast that changes these frequencies, it beats against the theta oscillation and it produces something like this. If you have multiple coexisting that sum together, you get a grid pattern like an hexagonal structure. So there is some evidence for this model. But it's interesting, I will add the slide here because 2 lectures ago, we saw this model of grid cells based on toroids, right? So that's a completely different model. That one explains, well, why grid cell fire in an hexagonal pattern. It can explain that. And it can explain why 2 grid cells always preserve the same geometrical relationship. That is, that if one grid is offset to the other, that kind of offset is always the same in every environment. And we discussed this. But that model doesn't explain phase precession. You would need to add things to that model. This model explains well phase precession. It also explains grid patterns, but it doesn't necessarily explain why 2 different grids remain aligned to each other. You would need to add things to this model. So this is really, and there are many variants of these models. So it's more like two families of models that are really competing. So I would say it's one of the hottest research question in this field is now figuring out which model is right, if any of the two, if either is right, because it's also possible that there are also other models. There might be other ways, but these are the ones that caught most of the attention. And people really putting a lot of effort and controversies in trying to demonstrate whether it's one of the model or the other model, the toroid model or phase interference model. Which one explains grid cells? Because I think it's just a quite complicated, extremely complex network that does these things. And as you hopefully have appreciated throughout this class, it's really an exciting topic that can allow us to understand how cells in the brain, while fighting to each other, they create things like a spatial representation or spatial cognition or things like that, right? So now, in the last 15 minutes, I want to move to this other topic, which is encoding of time intervals in spatial cells. So it's another way of thinking of time in hippocampus. So spatial cells means place cells and grid cells. So, okay, place cells, grid cells fire in, okay, there is a comment here. It's pretty incredible how comprehensive and the most basic functions are, definitely thought-provoking. Yes, this is a basic function, space. And the space, as we've seen from the very first lecture, it's an abstraction of your sensory motor experience. We went over and over, these are not just sensory cells, right? So there is an abstraction. Somehow these circuits are able to abstract your sensory motor experience into something that at this point we can call cognitive. So space, in a way, it's the simplest cognitive function I think you could study, because you can identify it very well behaviorally, and it's easy to correlate the activity of a neuron to the position of an animal. So it's amenable to, it's tractable, it's experimentally tractable. That's how we use, in our lingo. It's an experimentally tractable system. But, it just means that then when you figure out how those cells work together, you potentially use it as a sort of Rosetta Stone for understanding how the brain does a lot of other things too. Maybe not. Anyway, going back to this encoding of time interval in spatial cells. So remember what we did last time? We talked about memory. I'm not going to go this, we already seen this, that we were mostly interested in this aspect, declarative memory of facts and events. I might have or might not have said that memories of facts is called semantic memory. There are place cells in the hippocampus. Okay, now you know that. That's a fact. It's a semantic memory, okay? If you remember this, it's a semantic memory. But events is more like what happened to you, something that happens to you. Oh, I learned about place cells at that class, with called space and time in the brain. I remember. So that's more an event. It's called an episode. It's called episodic memory. So in a way, we think maybe episodic memory over time, they coalesce into semantic memories, but let's not go there. This is, if you're interested in that, there are classes here that are being taught about memory and learning and the neuroscience of memory and learning, which will cover a lot of the things that we covered here, but here we kind of more focus on space. So what is episodic memory? Well, classically, an episodic memory is defined as something that has a what, a where, and a when. Example, I parked my car on campus this morning. What, where, and when. I took a class on place cells at UTSA during the COVID-19 pandemic. What, where, and when. So it's kind of episodic memory. And so in a way, the brain has to have a few if you want to study these things and be informed by these psychological concepts, it has to have a way to encode the what, where, and when. Well, where, we studied so much about it, right? Almost everything we've done so far in this class is about how to encode where with place cells, grid cells, head direction cells, boundary cells, and phase precession today, and whatever. The what is something that I wish I had expanded a little bit more in this course. Is the idea that what O'Keefe and Nadell said, it's a memory system for interrelating, providing a spatial framework for interrelating the items and events of an organism's experience. What is these items and events other than space? Well, places can be modulated by many other things, which you haven't really seen, although we mentioned that here and there. Again, that's something that I wish we had expanded more, but one of you in their presentation will present object cells in the lateral entorhinal cortex, which project inputs to place cells. So like how place cells could start encoding both place and objects might be a little clearer when, it's something that basically it's a spin-off topic that we'll cover in one of the presentations. I forgot if it's like next week or November 30. But anyways, so we haven't really covered the what, but there is a what. Now it's when. Well, how do you encode time? And well, there are some theories about how place cells encode time. One would be like as a slow drift of the code. So remember when we started remapping last week, place cells can remap in multiple environments and have different maps, different environments. In a way, that might be going on also within the same environment slowly. So place cells becoming silent and active, place cells maybe remapping, even slowly on a slow time scale, as if like this is constant change of the spatial code that somehow could add the temporal dimension to the cognitive map. This is something very new, it's still controversial, it's very speculative, so we're not gonna go there. I mentioned this here, you should know that there is that idea. What we're gonna see now is more like how these cells can have been found, and it's fascinating, to encode the passage of time more in the sense of an interval of time, more like a stopwatch, right? So it's not like time from the beginning of time to the futures, like it's not like a calendar. All right, even the calendar starts again every year, but it's not like, the say BC and AC kind of time in the history of humankind. It's more like the time when, you have a competition sport events where you start taking the time with a stopwatch and you see when it comes. So it is about situations that are repeatable and they have a behaviorally defined starting point, and it's always the same. And every time you enter that circumstance, then these cells start coding the time interval, how time elapses. And this is what we're going to see better. So this was an experiment, and the details of the experiment, frankly, are not really that crucial, but the animal had to pay attention to an object, and then it has to stay in a confined position where there was a delay of several seconds, and then it goes to a different part of the task where it has to match and find the reward based on matching an order. So the orders were matched to objects, and the details of the experiments, I put them here, but they're not really that important here. What is important is that people recorded what place cells were doing while the animal was waiting, basically idle, not going anywhere during this delay. And what they found is that different cells become active at different points in time during that waiting period. So this is what you see here on these tracks here. You have different cells. You have a delay here, is that the x-axis that is shared on all these plots. It goes from 0 to 10 seconds. And so if you look at the firing rate in time of this cell, it goes up like this, right? If you go to this one on top, you'll see that the firing rate is very high at the beginning of the delay period, and then it goes flat. So you see, these are all the different trials and the different spikes on each trial. Each row here is a trial, you know, like all these occurring, all the experiments happening. And you see that the spikes are always there at the very beginning of the time interval. These other cell here, the spikes are a little later. And so the firing rate goes up and down. These third cells are even later. This one is even later. So they function as a sort of stopwatch kind of cell. So whenever, say, this cell fire, you know you are about 7 seconds into the waiting period. The other one, you know, you're at the beginning. And you see that they become less and less precise in how they represent time, right? You know, they have like their larger, wider fields, as if the system was struggling to keep an accurate representation of time. So there was this very interesting situation. Here is like you look at the delay, it's kind of like the same representation. And there are like about, what, 30 neurons here from one. Each row is a different neuron, and they color coded when they're active. And then they order them sequentially. And you can see, you know, there is one that is active at the beginning, then a little later, then a little later, then a little later, then a little later. So if you were looking at all these cells and know what's happening, you would know, you would be able to decode the passage of time. But, so this was just kind of like an experiment. It says, okay, so place cells now can act as time cells. Now, in the delay there, it wasn't too clear what the animal was doing. So people may say, well, maybe the animal are moving around, and those are like very stereotype behaviors. So this might be like a place cell. Now, another experiments that they did was the animals going on a alternate loops through these maze, and whenever they got in the middle, again, the exact details of the experiments are not necessarily important, but what happened when they're in the middle, there was a treadmill, and the rat was running on a treadmill for, say, 10 seconds. And then they saw the same thing. They looked at, you know, with time, they found cells that start firing, say, about around the end of that period of time that the animal was running on the treadmill. But now they also know how distant the animal is running through. So like how much distance the animal has traversed on that treadmill, right? And so they can plot things both in time and in distance. And they found cells that are more sensitive to distance and cells that are more sensitive to time. So for example, here, the two top parts, when they're plotted to times, this is basically, each row is the same neuron, right? And the left plot is time, and the right plot is distance. And you see that when you plot it in time, the firing is very precise. It always coincides. But if you plot it in distance, it's just all offset. But there are other cells that when you equalize it by distance, you get the firing basically gets aligned. When you plot it in time, you have they're not aligned. So basically what's happening here is that you have some cells that are really, it's not that they're encoding distance, and because the animal is always running at the same speed, it looks like time. It's really time. whereas the other ones are really distant. So there are some cells that probably are responding to something like path integration, and other cells that are really encoding the passage of time. And so this experiment was able to look at both things at the same time, because the rat was waiting while running on a treadmill. So it wasn't going anywhere, but it was moving on a treadmill. The same thing happens with grid cells. So like same experiment, same kind of plots, and you see that what is plotted here is distance or time on a treadmill. And they're also reporting what the same cell, the rate map of the same cell as the animal was running in space, kind of a separate part of the experiment. So that you can see those were grid cells, right? Grid cells of different scale, but while the rat was running in a box. But here, the same cell, each of these is a different cell, on the treadmill, like you would see the cell firing at a certain point in time, or maybe having even multiple fields repeating in time, but always consistently. So it's like a grid cell in time. It produces a grid in time. You have all these vertices in time. It fires, say, at second 1, then at second 6, then again at second 15. Or something like that, like it's repeatable. So it's like repeating, instead of having repeating place fields, it has repeating time fields in time. And this is like, this is how far I want to go in terms of, doing this time representation by places and grid cells. So it's still under investigated. It's still like some people think, well, is it really time, or is it really sequences, or is it really place? And one of you has a presentation, Mercy, that will talk about exactly this controversy. But it's a phenomenon that is not as well investigated as everything else we've done, place cells and grid cells. But it is a phenomenon that's been around for 10 years, and it's generating a lot of interest. And so there is definitely this property that these place cells and grid cells are not just firing in space, but they're also able to represent other forms of behavioral experience. So that's it for today. Of course, I can stick around for questions, and I will clean up these slides and upload them probably by tomorrow. I will assign some readings so that it helps you also understand all this. And again, I'm not going to give you an assignment. The assignment is, start reviewing all the material and start asking questions, because we have a test in 2 weeks. Next week, there's going to be presentations. So I expect you to be there for your, fellow students. I think that's all. Let me know if you have questions.
Thank you, Professor. Have a good week.
Thank you. You do the same.
I just wanted to talk to you after everyone is left, if you have a second.
Okay. Yeah, absolutely.
Thank you so much. Y'all have a good rest of y'all's day. Thank you.
You're welcome. Thank you.